Hello and welcome to the Abingdon Physics YouTube channel. I'm Mr. Willoughby and today we'll be looking at EdExcel IGCSE Physics, Topic 8, Astrophysics, Motion in the Universe. In today's video we will be covering these 5 spec points, 8.2, 8.3, 8.4, 8.5 and 8.6. So if you want to pause, I'll give you a moment now. The first spec point is really about understanding the scale of the universe. In our solar system, there are 8 planets. In our galaxy, there are billions of other solar systems, all orbiting different stars. And in the universe, there are billions of galaxies. Spec point 8.3 states, understand why gravitational field strength G varies and know that it is different on other planets and the moon from that on Earth. We know that the gravitational field strength on Earth, G, is equal to 10 newtons per kilogram. But what causes that gravitational field strength? Well, in reality, it's the mass of Earth. Now, we know also that different planets have different masses. So, the heavier a planet is, or the larger mass a planet has, the greater the gravitational field strength will be on the surface of that planet. As we get further away from the centre of mass of the Earth, the gravitational field around the Earth is going to become weaker. Therefore, as we move away from the Earth, that gravitational field strength is going to decrease. We should also know that gravitational force causes moons to orbit planets, causes the planets to orbit the Sun, causes artificial satellites to orbit the Earth, and causes comets to orbit the Sun. If we were to look at the moon's orbit around the Sun, it is effectively perfectly circular. This is because as the moon stays the same distance away from the Earth at all times, the gravitational force acting on the moon by the Earth is effectively the same at all times. Therefore, the moon keeps the same radius around the Earth. This is exactly the same as artificial satellites orbiting the Earth, and this is exactly the same as when the Earth orbits the Sun. Both will cause circular orbits because that gravitational force is the same throughout. Comets, however, will orbit the Sun in an elliptical pattern. So we've now described that both moons and planets have circular orbits because of that constant gravitational force around them. However, comets have an elliptical orbit. This is because their gravitational force acting on them by the Sun is constantly varying. The elliptical orbit will look a bit like so. Now the comet will be fastest at the point closest to the Sun because the gravitational force will be the strongest there. Now the comet will be slowest at the point furthest away from the Sun, and that's because the gravitational force will be weakest because the centre of mass of the comet and the centre of mass of the Sun are the furthest point apart. Now let's do a couple of questions based on these. Which of these is a large collection of billions of galaxies? Well, that should be D, the universe. Which of these is a correct unit for gravitational field strength G? That is newtons per kilogram, D. And which statement explains why the gravitational field strength on the moon is less than the gravitational field strength on Earth? And that is because the moon has less mass than the Earth. So describe the differences between the orbit of the moon and the orbit of a comet. So first off, the moon is a circular orbit around a planet, and the orbit of a comet is an elliptical orbit around a star. We should be able to get both marks with the drawing here. However, adding some more detail in the writing below is always a good idea. And here is the mark scheme for that question. We would have got 2 out of 2. In our next question, we have a comet orbiting a star because of the gravitational force between the comet and the star. Draw an arrow on the diagram to show the gravitational force acting on the comet due to the star. Well, that should be an arrow straight from the comet towards the star. Weight is another term used for gravitational force. At point A on the diagram, the comet has a weight of 4.4 times 10 to the 9 newtons, and the comet has a mass of 2.2 times 10 to the 14 kg. Calculate the gravitational field strength at point A. Well, we should be using the formula weight equals mg, always writing out our equation, and then substituting the numbers from the question into our equation. Rearranging our equation like so, we should get that G is equal to 2 times 10 to the minus 5 And we mustn't ever forget our unit, which is newtons per kilogram. And here we have our mark scheme, which agrees with the working that we have just done. On to our next question, where we have a comet orbiting a star because of the gravitational force between the comet and the star. And the comet moves from point A to point B during its clockwise orbit around the star. So explain what happens to the gravitational force acting on the comet due to the star as the comet moves from point A to point B. Well, my first thought on any one of these types of questions is how can we link it to an equation? So the equation for gravitational force, which we've already stated before is weight, is W equals mg. So how is the mass of the comet going to change between point A and point B? Well, in reality, it's not really going to, so therefore we can say that the mass is constant throughout. On the other hand, how is g going to change between point A and point B? Well, point B is further away from the star. Therefore, the gravitational field strength will be lower, so the weight or the gravitational force acting on the comet due to the star will be weaker at point B. We can see the marking points here, where we would have got marking point 1, 2, 3 and 4. However, there's also a marking point 5 where the direction of the force will change, and that's because B is now further along than where A was, and so the direction of the force will always be from the comet towards the star. Our final spec point for this video is to use the relationship between orbital speed, orbital radius and time period. We know that orbital speed equals 2 times pi times orbital radius all over time period. And in reality, this equation is just speed equals distance over time. So I'm going to look at an example of the Earth and the Moon. So I will draw the Earth below here, and then we have the Moon slightly above. The time period for the Moon to travel around the Earth is 1 day, and the distance the Moon travels in that day is simply the equation 2 pi r. And that's because the Moon travels in a circle around the Earth. And that value r is the distance from the center of the Earth to the center of the Moon. And it's really important that we remember that. And when we look at questions, we need to make sure we're using the center of the Earth to the center of the Moon. Now let's look at a question where we would use this equation. So we have the International Space Station, ISS, is a station that orbits the Earth at a height of 409 kilometers above the surface of the Earth. The ISS has an orbital speed of 7.66 kilometers per second and a period of 92.7 minutes. Calculate the orbital radius of the ISS. So we start off by writing out our equation, V equals 2 pi r over t. Now we would normally convert kilometers per second into meters per second. However, I can see that my answer wants it in kilometers, so I'm going to leave kilometers per second as they are, but 92.7 minutes does need to be changed into seconds. So after substituting my values into the equation and then rearranging, I obtain a value for orbital radius which is equal to 6,780 kilometers. Now part II asks us to calculate the radius of the Earth using your value for the orbital radius. What we need to remember is we've worked out the distance from the centre of the Earth to the centre of this space station. That distance was equal to 6,780 kilometres. We are also told that the satellite is 409 kilometres above the surface of Earth. Therefore, we must do 6,780 minus 409 kilometres, and this gives us 6,370 kilometres to 3 significant figures. And I'll give you a moment now if you want to look at the mark scheme. You can see it as similar to how we have done it. Thank you for watching the first Abingdon Physics YouTube video. Please like and subscribe. It will really help us out, and it will definitely help out your IGCSE Physics EdExcel knowledge. We'll be continuing to put more videos out soon. Thanks for watching.